in theory, that's what would happen. Hey guys, so this is our project. It's about Angry Birds, and for those of you who aren't familiar with Angry Birds, the main objective is to basically kill this pig using birds and a slingshot. But for our experiment, we used a pole and bungee cords and a basket for our projectile launcher. We were going to use that to launch the bird to hit this pig. Now, in order to do this, in order to calculate everything, first we had to measure out the distance from our experimental setup to the pig, which was about 12.95 meters. Then we measured the height from the ground to the projectile launcher, which was about 0.207 meters, and we also took about 5 trials to determine the average time it takes for the bird to hit the pig, which is about 1.32 seconds every single time. That's about the average. So in order to determine the initial velocity, which is what we're looking for, we first had to determine the initial launch angle. In order to do that, we use simple trigonometry, which is first taking the height, which is 0.207 meters, and the we took the distance here, which was 0.307 meters, and we used simple trigonometry, which was to figure out this angle, which is our initial launch angle. So the tangent of theta equals opposite over adjacent, and the inverse tangent of opposite over adjacent equals theta. So the tangent of 0.207 meters over 0.307 meters equals 34 degrees. Now this angle here is the initial angle we would have to have for our projectile launcher in order for our bird, which is traveling down at G, to hit this pig and essentially kill it, or in theory, that's what would happen.
Hey guys, we're going to start by calculating our required initial velocities for our shot to work that lasted 1.32 seconds and hit the pig that was 12.95 meters away using our projectile launcher. We're going to start by writing down the first kinematic equations that would apply to this experiment. We have our delta y and our delta x. Now we're going to rearrange these equations because we know these values, but we do not know our initial velocities in the x and y direction. So we're going to rearrange them to create these equations, and we're going to simply do that by here we subtract this term and divide by time, as you see here, to have initial velocity in the y direction by itself, and then for the x direction we just divide by time to have the x velocity by itself. Next, we're going to plug in the values that we know, which is Earth's gravity, the time that our shot lasted, our delta x, how far our pig was away, and how high our launcher was. So delta y here is going to be 207 meters. That's going to be subtracted. Negative g is going to be negative 9.81 meters per second squared. That's going to be divided by 2 times our time, which is 1.32 seconds squared, all over our time of 1.32 seconds. And this value equals, after we plug it and chug it into our calculator, is 6.62 meters per second, which is equal to our initial velocity in the y direction. For our x direction, we simply take our delta x, which was 12.95 meters, and divide it by the time it took to cover that delta x, as 1.32 seconds, and we get that our initial velocity in the x direction is equal to 9.81 meters per second. I know this value looks like gravity, but it's actually not. It's just coincidental that our numbers worked out this way. So when we draw our vectors, we had a vertical component, which we calculated to be 6.62 meters per second. Our horizontal component was 9.81 meters per second. And we are trying to find the initial velocity we had to launch it, and we calculated that we were going to do this at 34 degrees when we were doing it in the rack and ball room on Earth. So to calculate first this component right here, we're going to do Pythagorean theorem, which is a squared plus b squared equals c squared. Down here, 6.62 squared plus 9.81 squared is going to be equal to that c squared right there. If we take the square root of both sides, we're going to get a c that is going to equal 11.83 meters per second. So, in other words, we had to stretch our slingshot for it to produce an initial velocity of 11.83 seconds for our shot to work. Now, to check if our angle was right with our calculations right here, we can do the tangent of these two values to see if they compare to be 34 degrees. So 6.62 over 9.81, and the inverse tangent of this is actually equal to 34 degrees. So our math checks out, and these are our results.
If we wanted to achieve the same goal of having the bird be in air for 1.32 seconds and covering 12.95 meters, but being on the moon, our angles will have to change and our initial velocity, because the moon's gravity is lower than Earth's gravity, and you would have to shoot at a different angle to achieve the same goal that we were after. So in the same way we found our values for Earth, we're going to use the same formula in the moon, with our delta y of being 0.207 meters minus our negative gravity of the moon, which is 1.624 meters per second squared, divided by 2, multiplied by 1.32 squared, divided by 1.32. We found this value to be 1.228, and for our x value, we expect it to be the same because our delta x has not changed and our t has not changed. So we should have the same value of 9.81. Now when we draw our vectors, we have 9.81 as our x and 1.228 is our y. Now we are after two goals: to find our hypotenuse and to find our angle. So if we do the inverse tangent of 1.228 divided by 9.81, we find our angle to be 7 degrees. And now, to find our hypotenuse, we will use Pythagorean theorem, a squared plus b squared equals c squared. So 9.81 squared plus 1.228 squared is equal to c squared. And once we square root this, c is going to be equal to 9.88. Now, for Earth, we found this value to be 11.83 and our angle to be 34 degrees. Now we can see how they compare. On Earth, we needed a larger velocity than on the Moon. This is because more gravity is acting on Earth, well, when you're on Earth, than when you're on the Moon. And you would have to shoot it higher so it could cover the distance of 12.95 meters because there is a larger gravity.
Alright, hi guys. We've already done the calculations for the Earth and also the Moon. Now we're going to do our calculations for Neptune. So what we've got is our previously derived equations for velocity in the y and velocity in the x direction. The nice thing about the velocity in the x direction is that it always stays the same because we're covering the same distance in the same amount of time. So this still ends up being 9.81 meters per second. For our velocity in the y direction, we have slightly different values. The t and our delta y stay the same, but the g for Neptune is different. So what we're going to do is we're going to go ahead and plug these in. So what we have here is we have 0.207 meters. We subtract it from the negative g on Neptune, which actually is 13.3 meters per second squared. Divide that by 2, and then we multiply by time squared, which is 1.32 seconds. And then we divide the whole thing by time, which is 1.32 seconds. Once we plug our numbers into the calculator, we end up getting a velocity in the y direction value of 8.87 meters per second. So to find our resultant vector like we did for Earth and the Moon, we draw our little vectors here for velocity in the y direction, 8.87 meters per second. Velocity in the x direction is 9.81 meters per second, and we have to find this resultant as well as the angle. The way we're going to do the resultant is we're simply going to use Pythagorean theorem, a squared plus b squared equals c squared. Our c will end up being the square root of our a squared, which is 8.87 squared, plus our b squared, 9.81 squared. And so our c ends up being 13.22 meters per second. And then what we have to do to find the angle, we're just going to do the inverse tangent of our opposite over adjacent, which ends up being our y over our x. So that ends up being 8.87 over 9.81, giving us an angle, theta, of 42 degrees. We're going to go ahead and we made a chart. We're going to plug the values into the chart. And then 13.22. And as we can see, the theta and the r on Neptune much greater than both the Earth and the Moon. And then this is because, as you can tell, our g's actually is much greater on Neptune than it is on Earth and the Moon. So as our g gets smaller, as does our angle and our resultant.
Hey guys, this is our experimental setup. First, we have to calculate the Hey guys, so we're going to start off with our experimental setup.
Hi guys. Now most of you. Alright guys, now we're gonna calculate.
It's recorded.
Alright, so we're
Just
going...
say hi, guys.
Thanks, guys. Thanks, guys.
Thanks.
Yeah.
Appreciate you watching this. Okay, guys, thank you for watching our video. I can't do that. As soon as Ollie started bleeding.
Just stand.
Stop laughing.
Just
I'm not
stand.
gonna. Okay, guys, thank you for watching our video. If you have any questions, please email us, and we'll be looking forward to looking at it every other.
Thanks, guys.
Hope you enjoyed.
Really, bro?
That was actually a good one.
Can I do this part? Can I do this part? What am I saying?
Yeah, let her do
Let's
this
do
one.
that at the end.
She's got a cute voice.
Let's do that at the
I
end.
do have a
We sound like idiots.
What?
In a
What am I-
band. Dude, it can't be a planet.
Dude, it is a planet.
What's a planet?
Pluto.
It's not a damn
Yes,
planet.
it is.
It can't be a
It
planet.
is.
Dude,
Hey guys, what's up, man? Yay! What's up? Jenna, what are you
dude,
talking
dude,
about?
listen. Is Pluto a planet?
Yeah?
Dude, your anus is a planet.
No, man, Uranus is a
That's
planet.
disgusting. Dude, Pluto is not a planet.
Yes, it is.
Thank you
No,
guys
it's a
so much
planet.
for watching.
Listen,
We
my house
definitely
is so
appreciate
big.
it, and I hope you liked it.
Yeah.
Hey guys, thank you for watching our video. If you have any questions, please email us, and we'll be looking forward to watching everyone.